So we get to understand more and we become stronger in naming organic compounds. So this is the 10th example. As a 10th example, let us take a look at this question, and it is this. We have H, so we're told to name the compound this, that. Sometimes we may be faced with this kind of structure. This is what we call a seesaw structure. This is what we call seesaw. When you're faced with this kind of structure, what do you do? How do we name such kind of a compound? Now, do not fidget when you are faced with this kind of structure. It is the same thing as HO, and it is connected to C, double bond O. Another C is here, and another C is there with the methyl, that is CH3, and then we have another C down here, and then another CH3. So what we are trying to say in essence is, when you're challenged with this type of question, do not feel fear. This is what we call seesaw structure. It's called a seesaw structure. We're going to take that very well. Let us take that off properly. So what I want us to understand, dear students, is when you're faced with this type of question, do not fidget. Just understand that there is carbon here, there is carbon here, there is carbon, there is carbon, and we have another carbon. So we have 5 carbon atoms there, and here is CH3. This is what it means. So just take note of that. This is what it means. So when you're challenged with this type of structure, do not feel fear. Just know that this is actually a compound that looks like this. HO, C, double bond O, C, C, CH3, and then C, and last of all, CH3. So this is how it looks like. Then you can only go ahead to complete the bonding. There will be hydrogen here, and here, and here there will be hydrogen, and here hydrogen, hydrogen, and this is already complete. So this is just how the compound looks like. So you may choose now to write the condensed formula. HO, OC, CH2, C, and then we have CH3 up and H down, and then we have CH2 and then CH3. This is just the compound. You see, if you wish, you may turn it around. CH3, CH2, CH with CH3 above, and then CH2, and lastly CH, COOH. So this is the compound. It's as simple as that. So we have just only brought it out. So what is the name of this compound? As you can see, there is COOH. There is COOH. The presence of COOH tells you it is an alkanoic acid, COOH. Whenever you see COOH, it's an alkanoic acid. It's an alkanoic acid. So this is just like RCOOR, RCOOH. This is just RCOOH. That is what it is, RCOOH. So all this here is our R, and then we have COOH. So that is just it. Now what do we do? What is the name of that compound? Now let us tend to draw. Let us put that compound now. Let us rewrite the structure. Let us put down the structure very well. So the structure is CH3, CH3, CH2, CH with a CH3 up there, and then we have CH2 and COOH. So this is the structure. It's as simple as that. So what do? We simply know that our COOH is a functional group. This is a functional group. So preference is given to it because we ought to start from here. 1, 2, 3, 4, and 5. So that is where we start our numbering from, because that's a functional group. So it means that this is our side chain automatically, and this is the parent chain. There are 5 carbon atoms, and we have a functional group COOH. So it means that this is called 3-methyl. We have to erase that. It's not cleared. So let us name that again. So this is called 3-methyl. There are 5 carbon atoms there. Since there are 5 carbon atoms, it ought to be pentane. It ought to be pentane since there are 5 carbon atoms there. But because we have COOH as a functional group, then we'll remember what we saw when we were discussing alkanoic acids or carboxylic acids, which have COOH. The rule says that in naming an alkanoic acid or a carboxylic acid, that the E in alkanes are usually replaced with oic acid. The E in alkanes will be replaced with oic acid. So instead of having it as 3-methylpentane, since there are 5 carbon atoms there, the E will be replaced with oic acid because of the presence of COOH. COOH is a functional group. So the name is properly called 3-methylpentanoic acid. So that's the name of the structure. So don't get frightened because of what we have there. Don't get frightened because of this structure. Don't get frightened yesterday. So when you see a structure like this, this is what we call a seesaw structure. It is called a seesaw. When you see structures like this, it is called a seesaw structure. Don't get confused. Only have to know that this is carbon, there is carbon here, carbon there, and carbon there. So you only have to put the hydrogens that should be attached to them to make it complete 4 bonds for each of the carbon atoms. 4 bonds for each of the carbon. Sometimes they may even come with double bonds. Sometimes you may see them with double bonds. And it's the same thing. It's still the same alkene. Or even if you see them with triple bonds, it's the same thing with alkyne. So only what you do is you can straighten it up. C, double bond C, single bond C, double bond C, and single bond. That is just it. So this is just how it is. You may wish to straighten it up just as we have seen. So this is actually how organic compounds are named. So we can see, having seen the seesaw structure, we have analyzed it down, derived what it looks like, and now we've gotten the name. The name is 3-methylpentanoic acid. Okay, so having seen that, let us proceed. Let us look at another example, and that will be 11. Let us look at another example. That will be 11. So just like that, the one above, let us take a look at this compound, HO. So we have this, and we have this. So we can see so we have this. Good. So this is the compound. So we can see this is an example of a compound where there is double bond between the carbon atoms. So when you see something like this, you don't need to fidget. All you need to do is bring out the carbon atoms that are there. So this compound can be written as HO C double bond O C C and then double bond C. Can you see that? So it's as simple as that. It's as simple as that. So that is the compound. So look at it. It's a compound. This is just it. So you only have to put C at each of the points, at each of those junction points. Just put your carbon at each of those points. Now the next thing you ought to do is complete the bonding for each of the carbons. So we have our compound. Let's try to erase that first. So we have our compound above as HO C. Let's try to erase this. That is not coming out clear. So we just have to take it up a little. So we have this. So let's see how to bring out our compound HO. We are trying to now complete the bonding for each carbon. Each carbon ought to have 4 bonds. And this first carbon we are seeing is complete. So for the next, we have hydrogen up here. And hydrogen also will be here to complete 4. And then we have the next up. It's having a double bond with this. So it means we can attach 1 hydrogen to this to make it 4 bonds. And for the last carbon atom there, it's having 2 bonds already. So we have to attach 2 more hydrogens to complete 4 bonds for it. So, and that is it. This is how to complete that. So now you can condense this. Condense it as in HO, OC, CH2, CH, and then CH2. Or you have to indicate the presence of the double bond. There is H, and then there is a double bond there. Double bond CH2. So that is it. You see that? So this is the compound. You may wish to flip it the other way by saying CH2, double bond CH, and then CH2, and then COOH. You can say we only just flipped it the other way. So it's the same thing. So having seen that, what will be the name of the compound? So when we see compounds like this, you don't need to fidget. You don't need to say, I've not seen this type of structure, or I have not been taught this type of structure. It is all the same thing. It's still your carbon atom. So what will be the name of this compound? Looking at the compound there, we have a double bond, and we also have the COOH. The COOH there is our functional group. It's a functional group. So since it is a functional group, preference will be given to the COOH. So this is COOH. It is a functional group. So preference is given to it. Why? Because it is higher than the double bond. Double bond is also a kind of functional group. It's a functional group. But because there is COOH, preference will be given to the COOH. So we'll begin our counting from the COOH. 1, 2, 3, and then 4. 1, 2, 3, and then 4. So it means our COOH will end the name of this chain, and then the double bond also will be recognized. Now our double bond falls under carbon 3 and carbon 4, between carbon 3 and carbon 4. So since the double bond falls under between carbon 3 and carbon 4, the name of that compound will be 3-butene. Now, consider this. It ought to be 3-butene because the in, which is a double bond, falls between carbon 3 and carbon 4. And then we have said that for such cases, the lower number, the lower carbon atom will take the ownership of the double bond. So since 3 is lower than 4, 3 takes preference of ownership of the double bond. So the name of this compound ought to be 3-butene. But because we have COOH there. The COOH tells you now that the in will not end the name. That is, it is not just only an alkene. It cannot end the name because COOH is the main functional group, which is going to end as a parent chain. So it otherwise means that this compound is an alkanoic acid. It's a carboxylic acid compound. But it's only a carboxylic acid with a double bond. So the double bond there is only going to be represented. We're only going to say where the double bond is found. It is found between 3 and 4, but 3 takes the name. So automatically, since this is an alkanoic acid, like we said before, the E will be replaced with oic acid. So we only have to say oic acid. So the name of that compound is 3-butanoic acid. So you just have to combine it and say it is 3-butanoic acid. So that butene in tells us that there is the presence of a double bond there. It is not butanoic acid. It's not butane. It is not a single bond. If it is a single bond, it could have been 3-butanoic acid, as in it could have been 3-butane. You see that? Then oic acid. If it were to be a single bond, it could have been 3-butanoic acid. But since it is not there, since it is not like that, and even it cannot be 3-butanoic acid because alkanes don't have double bonds. Are you seeing that? So because of that, we ought to understand. I just want us to be clear. Alkanes doesn't have double bond. So this tells us that the compound is an alkene, but it is an alkanoic acid with a double bond. And that is why its name is 3-butanoic acid. 3-butanoic acid. So that is our answer to that compound. So having seen that, let us take a look. And now I'm going to give you the last example. Dear students, I think with all these examples, you should be able now to be very, very strong in